All right, let's dive right into this explainer. We hear the word cloud tossed around all the time, right? We upload our photos to the cloud, our business databases run in the cloud, we stream movies straight from the cloud. But here is the truly fascinating part. The cloud is not some magical, weightless ether floating above us. The cloud is heavy. It's actually made of spinning metal cladders, microscopic lasers, miles of magnetic tape, and incredibly complex silicon circuitry. So today, we're taking a journey to understand exactly how our digital data is physically stored. We'll be doing a clear overview of the fundamental engineering behind external memory, giving you a really comprehensive look at the physical reality of your digital footprint. Here is our roadmap for today. We'll be hitting 5 key areas. First, the foundation of magnetic disks. Second, the teamwork of the RAID system. Third, the speedster, which is solid state. Fourth, the archives, optical memory. And finally, deep storage using magnetic tape. At every single stop, we'll see how engineers battle to balance 3 crucial things: massive capacity, blistering speed, and rock-solid reliability. Okay, Section 1, the foundation, magnetic disks. Let's start with the absolute workhorse of the modern computing era. If you've ever used an old-school vinyl record player, well, you actually already have a great conceptual model for this, just on a microscopic scale. Instead of a physical needle in a groove, a conducting coil, called a head, hovers just fractions of an inch above a rapidly spinning platter. To write data, electric pulses are sent to the write head, which is basically a tiny electromagnet. This creates a magnetic field across a tiny gap, which then magnetizes a small area of the platter zipping beneath it. Positive and negative currents create different magnetic patterns. Boom, there are our ones and zeros. To read it back, modern drives use a completely separate hypersensitive magnetoresistive, or MR sensor. That sensor detects those magnetic changes as electrical resistance, converting them back into voltage signals. It's pretty brilliant. Now, you can't just throw data onto a platter completely randomly, right? Because the stationary head only reads what passes directly beneath it. Data naturally organizes into tight concentric rings called tracks. Picture thousands of these rings packed unbelievably tightly onto a single surface. And to prevent magnetic interference, or prevent major errors if the head gets even slightly misaligned, tiny gaps sit between these adjacent tracks. The precision here is absolutely astonishing. I mean, imagine keeping this perfectly aligned while the platter is spinning thousands of times per minute. But how do we actually measure all this data as it's zipping by? We don't just grab a whole track at once. That would completely overwhelm the system. Instead, tracks are chopped up into sectors. Think of a sector as the fundamental, bite-sized chunk of data. It usually holds 512, or in newer systems, 4,096 bytes of user data. And just like the tracks themselves, sectors are separated by tiny intersector gaps, so the hardware doesn't have to be impossibly precise. Moving on to Section 2, teamwork, the RAID system. Because look, magnetic disks are incredible, but they definitely have physical limits. There is a maximum speed a platter can spin before it literally shatters. Plus, because they rely on mechanical moving parts, eventually they're going to break. Which leads us to a pretty massive question. Think about a giant enterprise database or a massive video streaming service. What happens when the speed and capacity of one single physical drive simply isn't enough to handle the demand? Well, the answer is RAID, the redundant array of independent disks. This is literally the ultimate teamwork concept in computer architecture. Instead of relying on one super expensive, giant, fragile disk, RAID takes multiple independent physical drives and links them together, so the computer's operating system just sees them as one single logical drive. By striping or splitting data across multiple disks, we can read and write to all of them at the exact same time, which massively boosts speed. And by using some extra space to store parity information, which are basically mathematical backup clues, we guarantee that if one physical disk literally catches fire, we can fully rebuild the lost data from the surviving drives. Of course, this teamwork involves some major engineering trade-offs depending on the RAID level you choose. Take RAID 0, for example. It spreads data across all drives for maximum possible speed, absolutely perfect for high-bandwidth tasks like 4K video editing. But there's zero safety net. If one drive fails, the whole shebang is gone. On the other extreme, we have RAID 6, which provides extreme fault tolerance. It can survive multiple drives dying at the exact same time by computing 2 completely different parity algorithms. It's the perfect, albeit slightly slower and more complex, solution for something like a mission-critical bank database. All right, Section 3, the speedster. Solid state. Because even with all that RAID teamwork, the sheer mechanical friction and rotational latency of physical hard drives became a huge bottleneck.
Enter the solid-state drive, or SSD. Like we talked about, magnetic disks are fundamentally mechanical. You literally have to wait for a robotic arm to move and a physical platter to spin. But SSDs, they rely on purely electronic semiconductor magic using NAND flash memory. Zero moving parts, no spinning, no seeking, just instant, pure electronic data retrieval. The real-world impact of ditching those moving parts is absolutely staggering. File copy speeds leap from a sluggish 50 to 120 megabits per second on a traditional hard disk, all the way up to 550 on a standard NAND flash drive. Even better, SSDs average just 2 to 3 watts of power draw, which is less than half of a mechanical drive. That exact efficiency is why swapping to an SSD literally instantly gives your laptop a longer battery life. Now, the trade-off, historically at least, has been cost and total capacity, with SSDs costing significantly more per gigabyte, though, to be fair, that gap is rapidly closing. Section 4. The archives, optical memory. Let's zoom out a bit from the internal drives of our computers and talk about removable media. How do we easily and cheaply distribute software, movies, or music to millions of people? Optical memory. Down at the microscale, optical memory works completely differently. Unlike a magnetic disk that alters tiny magnetic fields, an optical disk physically stamps data into a clear polycarbonate plastic surface. A highly focused laser shines up at it. When the laser hits a flat surface, which we call a land, the light reflects back brightly. But when it hits a slightly recessed pit, the light scatters. A photosensor reads these bright and dim reflections as digital ones and zeros. And since it's really just stamped plastic, it can be mass replicated and manufactured for literally pennies. But as our media evolved from standard audio to high-definition video, engineers had to figure out how to squeeze way more data onto the exact same size disk. The trick? They changed the light itself. A standard CD uses a 780 nanometer infrared laser, but Blu-ray uses a shorter 405 nanometer blue-violet laser. Because that beam spot is dramatically smaller, the pits and lands can be packed incredibly tightly. That simple change boosts a single layer's capacity from 680 megabytes on a CD to a staggering 25 gigabytes on a Blu-ray. And finally, Section 5, Deep Storage Magnetic Tape. For our last tech stop, we're actually looking at the oldest technology in our memory lineup. Now, you might think magnetic tape died out with the VCR, but no way. It absolutely survives today, and actually, the world's biggest tech companies rely on it heavily. Why? Because it offers the absolute lowest cost per gigabyte of any storage medium out there. With modern linear tape open, or LTO-8 formats, a single cartridge can hold up to 32 terabytes of compressed data. It's removable, meaning you can pull it out, stick it in a fireproof vault, and have a safe archival backup completely disconnected from the internet. The one catch? It's a sequential access device, meaning if you want a file at the very end of the tape, you literally have to fast forward through the whole spool to get there. So yeah, it's slow, but for deep data archives, it is undefeated. To make this as efficient as possible, modern systems use this incredibly clever trick called serpentine recording. Instead of writing data straight across like a typewriter and then awkwardly rewinding the whole spool, the drive records the first track along the entire length of the tape. When it hits the end, the head just shifts down a tiny fraction of a millimeter and writes the next track entirely in reverse. It just snakes back and forth until every single inch is packed, maximizing all the available space. So, from spinning magnetic platters and lightning-fast solid-state silicon to microscopic laser pits and miles of serpentine tape, the cloud is a very physical, highly engineered reality. We are constantly playing this game of balancing speed, capacity, and cost. But here is the major takeaway from this explainer. Humanity is generating new data at a rate that is, frankly, terrifying. And we are rapidly approaching the physical limits of just how tightly we can pack atoms together. As our digital footprint continues to explode, what physical marvels will we have to engineer next to store it all? Are we looking at DNA storage, quantum memory? The next chapter of external memory is being written right now. Thanks so much for joining me on this deep dive into the physical world of digital data. Keep questioning, keep learning, and I'll catch you on the next one.